Good morning, students. Today we are going to discuss a few important topics from the chapter 4, and the chapter 4 is your moving charges and magnetism. Now the topic which we are going to discuss is your Lorenz force. Now this is some kind of force where both electric field and magnetic field exist. So let me try to explain it in details. Suppose a charged particle is moving in a region where both electric field and magnetic field is there. So what will happen? The electric field will try to accelerate the charged particle, and the magnetic field will try to change the direction of motion. Basically, it tries to make a curved path if the charged particle is moving in a straight line in the absence of magnetic field. But when you apply magnetic field, a force will exert and it changes the direction of motion, or it changes the track. The nature of the track will change due to the presence of the magnetic field. So if a charged particle experiences both electric force as well as magnetic force, then the total force can be defined as your Lorenz force. Now let me try to read out what we have written. When a charged particle having charge q moves in a region where both electric field E vector and magnetic field B vector exist, it experiences a net force called Lorenz force. And the Lorenz force is nothing but the sum of the force experienced by the charged particle from electric field as well as magnetic field. So if it is only electric field, then the force is your q E vector, and if it is magnetic field, then the force is your q V vector cross B vector. So already we have defined this two term in previous chapter or previous class. So the force exerted by charged particle due to the presence of both electric field and magnetic field can be defined as your Lorenz force. Now next topic which we are going to define is your Fleming's left hand rule. This rule is very important to define the direction of the force experienced by a charged particle when it moves in a magnetic field. Now when a charged particle moves in a magnetic field, what happens basically? The charged particle produces current because charged particle is in motion. So there is a current. Now whenever there is a current, there is a magnetic field as per from Oersted experiment, and there is already an existing magnetic field. So two magnetic field interact, and as a result the charged particle will experience a force, and the direction of the force can be defined by Fleming's left hand rule. Now what is that one? If you hold your left hand such that three fingers are mutually perpendicular to each other, the first finger, the central finger and the thumb. Now if the first finger points along the direction of the magnetic field and the central finger points along the direction of the current, then the thumb gives the direction of the force. So what we have written, let me read out. If first finger points along the direction of magnetic field and central finger along the direction of current, then thumb points along the direction of force, provided the three fingers are mutually perpendicular to each other. So the first finger is along the direction of the magnetic field, the central finger is along the direction of current, then the thumb gives the direction of the force, provided these three fingers are mutually perpendicular to each other. So this is your Fleming's left hand rule, and we are going to use this rule later on to define the direction of the force. Now the next topic is very important, force on a current carrying conductor. Now here we are considering a conductor of length L, and the conductor has free electron. So the electron is moving with the drift velocity v suffix d along y dash. So electron is your negative charge, so opposite to the direction of the negative charge there is a current, so the current is along the positive y-axis. And magnetic field is there, that is your Fleming's, that is your z direction magnetic field. So current is along y direction and magnetic field is along z direction. So if you apply Fleming's left hand rule by pointing the first finger is along the direction of magnetic field and the central finger is along the direction of the current, then the thumb points towards you out of the plane, gives the direction of the force. So each electron will experience a force, and that force is given by F equal to small f vector equal to minus E v d drift velocity vector cross B vector. as per from force already we have defined in our first class of this chapter. So total force we are trying to define. So total force, this is the force on a single electron, so you have to count the total electrons in the conductor, and for that you have to count the volume. Volume is your area of cross section into length, and force, total force we have given capital N F vector, and N is nothing but the capital N is nothing but the total number of electrons present in the conductor. So total number of electrons, if you consider small n is your number of electrons per unit volume, then the volume of this conductor is your AL. So small n, capital A, small l gives you the total number of electrons, and the total force is your nothing but capital N into the force on a single electron. So F vector comes out to be your, substitute the value of n. So n is your small n, capital A, small l, and F vector is your, small f vector is your minus E Vd vector cross B vector. Now let me try to simplify this equation, and for that we have to go to the points number 3. Now if IL vector represents a current element, so this is very important one, current element. So if you consider unit current, then what is the current element? Unit current, for unit current the current element is only L vector, small l vector, no? If IL vector represents a current element, so vector symbol is only over capital L, okay, only over small l, not capital L, only over small l. If IL vector, small l vector represents a current element vector in the direction of current, current element vector is always along the direction of current, then this one L vector and Vd vector will have opposite direction. If you consider unit current, then it should be your L vector, no? So for unit current the direction remains same, it does not changes, no? If you change the magnitude, the direction does not changes. So if IL vector represents a current element vector, for unit current it is your L vector, no? And IL vector is along the direction of current. So for unit current it is your small l vector, so it is also along the direction of current. So if you see the figure, the direction of current and Vd vector is in opposite direction, no? So then you can say L vector and Vd vector will have opposite direction. This is the point which you have to understand. That is your IL vector. IL vector is your current element, and for unit current the direction remains same, is not it? So it is your L vector, small l vector. So small l vector is nothing but the direction of current, and Vd vector is in opposite to the direction of current. So L vector and Vd vector are in opposite direction. So you can give V suffix d L vector equal to minus L Vd vector. So you see the arrow part changes. If you put the arrow over small l vector, then it has one direction, and if you put the arrow over Vd vector, V suffix d vector, then it has opposite direction. So that's why one negative sign is given. So point number 3 is very important. You must have to understand this one. If you understand this one, then it becomes very clear. And IL vector is your current element. So if you change the magnitude of the current, I think direction of the current element will remain same. So if you consider unit current, then the direction of the current element is your L vector, is not it? And L vector is along the direction of current. The total product is your L vector, IL vector, if you consider I is your unit current. So L vector and Vd vector are in opposite direction. So if you substitute 3 in 2, then you can simplify further. So number 4, from 2 and 3, F is your NAE and minus L Vd vector cross B vector. So the negative sign we are taking out, minus L Vd vector, so Vd L vector. So Vd we have taken out. Now the product NAEVD, N is a number of electrons per unit volume, and Vd is your distance by time, you can consider. So total charge divided by time gives you the current. So NAEVD is your current. So ultimately you are getting the expression F vector equal to I L vector cross B vector. Now if you consider the magnitude part, it becomes your F equal to BIL sin theta, where theta is the angle between the direction of the magnetic field and the direction of current, because current element is along the same direction as that of the current, no? So theta is the angle between magnetic field and the direction of current. Now under note, we are trying to substitute the value for theta. If theta equal to 0 degree, then f is your 0, and if theta equal to pi by 2, then f is your BIL. So this expression is very important. Please go through this topic. These topics are very important for your exam point of view, and also for entrance related question also you will get from this topic. So this is all about. Please go through this topic and find out your doubts, and if you have any doubts, please put your doubts so that I can check it out. Thank you.